In this lab, we will build the logic unit. So last time we built arithmetic unit, which does some mathematical calculations, addition, subtraction, and so on. And in this lesson, we will make the logic unit, which will perform a logic operations and or not XOR on two numbers with each other. So let's go. So I have built this table in which I have assigned the operation codes to several functions that are supported by basically any microcontroller. So these are AND, OR, XOR, NOT, logical shift left, logical shift right, rotation left through carry, and rotation right through carry. So again, let's make a simple table where we assign the values to A, B, and carry in. So we have functions AND, OR, XOR, NOT, logical shift left, logical shift right, rotate left through carry, and rotate right through carry. So rotate right through carry would be arithmetic shift right. Okay, rotate right. So we again will have inputs A, B, and carry in. So to perform AND, we select for input A, just input A, for B, B, and for carry in, we don't really use it, so no, we don't use it at all. OR is going to be the same. A or B, and carry in isn't really used. XOR, to perform XOR, we use A and B, and carry in isn't really used. NOT is bit inversion. So we take A and just flip all bits to the opposite. So we use A, but we don't really use B or carry in. Logical shift left. So we will make a simple shifter. We will not do barrel shifting, just simple shift. Let's see. Okay, so logical shift left. We will not make barrel shifter, so we just take A and we shift bits by one to the left side, so we don't really use B or carry in. Logical shift right, the same, we only use A and not B or carry in. Rotate left through carry means that we shift all A bits to the left, but instead of pushing 0 into the first empty space, we will use carry in, and we don't really use B. And to do rotate right, again, we take A, we shift all bits to the right, but instead of pushing 0, we push in carry in. So we don't really use B, but we do use carry in. Okay, so now we need to make a logical unit that performs all of these operations. Some of them are very simple, but some of them are a little bit complicated, so we will build sub-circuits for some of them. So let's go to our project and add sub-circuit, which we will call logic unit. So it's right here. And similarly to arithmetic unit, from which we can actually copy and paste some parts, we will be using A, B, and carry in, and we will have carry out, for example, for logical operations, it's going to push out the top bit into the carry bit. And we will also have output Q. So let's place 8-bit input A facing south, copy it and rename the second input to B, and then 1-bit input which will be carry in, 1 bit facing south. So now we will also need a big multiplexer, and as you can see, the number of operations is 8, which means that we need to use a multiplexer facing south, no enable bit, select bits are 3, and data bits are 8. So we feed two 8-bit numbers, and it's going to select the correct operation. So we also need the input for operation selection. So select operation. Let's see, how did we name it here? All capital letters, so here also. Select operation. And its size is 3 bits because we have 8 different functions. So the first one is A and B. We can just select this AND gate. We use it with data bits 8, so it will do bit by bit on two 8-bit numbers. Size will be narrow, it will be facing south, and number of inputs is just 2. So in the first multiplexer's input, we will select this, which calculates A and B. Like this, and we will have output Q, which is also 8 bits, and its label is Q, and it's facing north, like this. So let's check out. With our operation selector, we selected operation number 0, which basically means this multiplexer forwards input 0 to the output, and operation. So we set some bits, and for B, some other bits. And let's see how it works. So 1 and 1 is 1, 0 and 1 is 0, 1 and 1 is 1. So basically, if in both inputs in certain location bit is 1, then output will also be 1, and in other locations, the output will be 0. So, you know, this AND function works. So that's check. Next is OR function. So what we can do is select under gates, OR gate, and do the same thing. So 8 bits facing south, size will be narrow, number of inputs just 2, label maybe OR, and this label AND, just so we see it and have less confusion. Okay, so OR output goes into the second select signal, and inputs will again be A and B. So it takes as inputs A and B, calculates OR. So when we select operation number 1, then it calculates OR on these two numbers. So whenever at least one of the input bits is 1, output bit is also 1. And only in the places where both inputs had 0, in that location, the output also has 0. So OR gate also complete. For XOR, we have the same. So it's facing south, data bits are 8, size is narrow, number of inputs is 2, label XOR. So we put it here, and one input is A, the other input is B, and the output is just fed into the third input of the multiplexer. So now, when we select operation number counting from 0, operation 2, it calculates, all of these are calculated, but only XOR is forwarded to the output. So A XOR B, the result is here. So if in both places the bits are the same, the output is 0, but if the bits are different, in one place is 0 and in the other is 1, then the corresponding bit will be 1. So 0 XOR 0, 0. So XOR function works. Next is NOT. It's just inverting of all A inputs bits. So we select NOT gate, we rotate it to point to south, narrow size, label NOT, and we only use A input in this case. So I also forgot to select data bits 8. And we feed it to the third, counting from 0 to the third or to the fourth input of this multiplexer. And now, if I select operation number 3, counting from 0, then it just inverts all A bits. This multiplexer is selected to forward that input, and here is Q. Q is the opposite of A. So NOT operation is complete. Now is the interesting part. Logical shift left, right, rotate left, and rotate right. So I could build it in this circuit, but unfortunately it would be a very ugly picture. So instead of trying to make these 4 functions here, I will make sub-circuits for them. So project add circuit, I will call it logical shift left. And here I will have 8-bit input A. So it's facing south. Data bits are 8. And label is A. So this is our input A. And now I also need output Q facing north with 8 data bits and name Q. And now I need to shift all of the bits of A by 1 to the left side. So which is the left side? Logical shift to the left would be to that direction. So from right to left. So to do that, I just need to use splitter. It has 8 bits in and 8 bits out. It will be facing south. So A goes in and I expand all of the bits. And now I have access to each of the bits. I create a second splitter. I rotate it. And now logical shifting means that all bits go to one position forward. So I just move this splitter one grid location forward. And so, sorry, like this. So shifting all bits 1 bit forward means that bit 0 becomes bit 1, bit 1 becomes bit 2, bit 2 becomes bit 3, and so on. And now, as we talked in the lecture, we need to figure out what do we do with the first bit and with the last bit. So logical shift left means that 0 is pushed to the bit number 0. So we push all bits 1 position to the left and feed in 0. So under constant, I select 1 bit constant facing south, and I just feed it right into the first location. And what do we do with the last bit? We store it in carry. So I need to make output called carry out, C out, facing east, and connect it like this. So the top bit will be just stored in carry. And this is our output. So let's check out. Let's say, for example, I have input 1, 1, 0, 0, 1, 0, 0, 1, like this. So all bits are shifted left. As we can see, 0 is shifted into the 0 position. So 0, 1, 1, 0, 0, 1, 0, 0. And the top bit is pushed out to carry out. So this is the first place where we are using this carry bit, but instead of pushing it in, we will store it in the status register. So let's edit its appearance. So here is our input A, here is our output Q, and here is carry out. So where could we put the carry out? Let's see, in arithmetic unit, it's located on the left side, so we will do it the same everywhere else. So in this sub-circuit view, basically I'll just leave it there, and I will put text logical shift left so that I see which block it is, like this. And now I go to logic unit. I click once on this logical shift left to place it on this schematic. So the input is A, the output Q is forwarded to the output, and there is this carry out bit, which is actually an output of the logic unit. And it needs to be stored in the special register, which is called status register, which we will learn about a little bit later. So I need to create a new output. For example, on the right side, it is output facing east. So that it is the same location as in this arithmetic unit. So in the logic unit, it will also be located, for example, here. And if necessary, I can say there. So it's gonna be facing east. Is it output? Yes, one bit. Label will be carry out. In arithmetic unit, it's just called carry out the same. Okay, so I could connect it like this, but you know that I will actually have carry out value in logical shift right, rotate left, and rotate right. So to connect it correctly, I would need to do multiplexer, which selects between carry out values. So to make it very simple, we will put another mux for carry out bit. And there is this convention that the arithmetic and logic functions that don't modify carry bit should just forward carry bit as it was in the previous state before the operation. So we create a multiplexer for carry in to carry out conversion. Its data bits will be 1, and for first 4 operations, the carry value that was before the operation should be forwarded to carry out after the operation, so that the carry bit is not modified. So, and the selector is the same for operations. So for example, if we do operation number 1, which is OR, if carry in was 1, it should be saved as carry out even though and or and XOR and not functions do not modify carry, to make sure that it's not modified, we feed it in and out. So we basically copy carry in bit to carry out so that these functions don't modify it, they don't update it. So, however, for function logical shift left, it modifies carry, and therefore the new value of carry will be saved in carry out. So let's see, we select operation number 4, counting from 0, which is logical shift left on A. And it doesn't matter what was the carry in, the carry out is calculated from this logical shift left block. So let's say I want to calculate, for example, logical shift left on this number 11001111. The output is 0 is pushed into the first position. Next bits are copied 111101, and the last bit 1 is forwarded to carry out. Okay. So to make it a little bit clearer, I will make a new column here, and I'll write what is the value of carry out. So for logical shift, for example, logical shift left, carry out is equal to a bit number 7 before shifting. So in logical shift left block, bit number 7 is forwarded to carry out. For logical shift right, we shift bits to the opposite direction. So it will be, for example, a bit number 0. And it's calculated inside the logical shift block. However, for and, or, XOR, and not, the carry out should not be changed relative to carry in. So basically carry out should be equal to carry in. Also in OR, it's equal to carry in. Basically, we don't update it, we don't modify it, we just copy carry in to carry out, because if we need it for other functions, it should just not be touched. And for not, the same, carry in. Okay, so now we need to make a logical shift right, rotate left and rotate right. So to have space for it, I'll move it like this. And let's create a new subcircuit, add circuit, logical shift right. So in logical shift right, we will actually just copy logical shift left contents to just have them faster ready. And now the shifting will just happen to the opposite side. So I need to select these cables and delete them because they are wrong. So in this case, to shift numbers to the right, I need to move the splitter by 1 grid location to the left. So logical shift right means that bit number 7 becomes bit number 6, bit number 6 becomes bit number 5, bit number 5 becomes bit number 4, and so on. So all bits are shifted 1 position to the right. 0 is shifted in to the top bit, and bottom bit is shifted to carry out. And I need to also select it facing west so that this active point is to the left, to the left side. Yes. So let's just check it out. Let's say I have number 11001010, and as you can see, 0 is shifted to the top location. Next bits are just copied, and the bottom bit is forwarded to carry out. Okay, so now I will edit the subcircuit, and I'll just move the carry out to the same side as we had it for logical shift left, so that they look the same. But I will add text logical shift right. Okay, so we go to the logic unit, click on logical shift right once, place it on the schematic, and I'll just edit these cables so that they look a little bit better. So the input of logical shift right is A. The output goes to Q, and the carry bit is saved in this multiplexer. So let's test it. We select operation number 5. It is logical shift right. And let's see, all bits are shifted to the right. And since the bottom bit was 1, it also, the carry out is set to 1. Okay. Finally, we need to create rotate left and rotate right through carry. So rotate left and rotate right is the same as logical shift left and logical shift right, but instead of just having 0 pushed in, we push in carry in. And carry out will be the same as for logical shift left and right. So under project, add circuit, I will add rotate left. I'll go to logical shift left and just copy its contents to rotate left. And instead of pushing in 0, I will create an input square box facing west with label carry in, and I push this value to the bottom. So if I set it, it's gonna push in 1, and other bits will be just copied. As you can see, top bit is pushed out, bottom bit is the carry in bit. So like this, and if I go to subcircuit view, I can see that outputs are in the corresponding places like this. And I'll just add text rotate left so that I know that this is rotate left block. I go to my logic unit, I click on rotate left once, I place it in the schematic. So for it to fit, I need to move these cables down. And also this plexer down. So Cabling is a little bit complicated here once the circuit becomes so big. So the input of rotate left is A. The output goes to Q. Carry in is taken from carry in, and carry out is forwarded to the output of this multiplexer. Cabling is a mess. Next is rotate left through carry. So let's test it out. So we have A, which is 1, 1, 0, 0, 1, 1, 1, 1. Let's see if I select operation number 6 out of counting from 0, it's operation number 6. So I have this A, rotate left means rotate left to the left side. And all bits are shifted by one position, and in the bottom position, carry in is copied. So if I set carry in high, the bottom bit is 1, and if I set it low, the bottom bit is 0. And the top bit is equal to carry out here. So rotation left through carry is working, and finally I will add circuit rotate right through carry. I take the contents of logical shift right, I just copy them to rotate right, and instead of this 0, I create input called carry in, and I connect it to the top bit so that carry in is pushed in, all bits are forwarded one position, and bottom bit is carry out. And in this sub-circuit view, I need to just swap input and output so that it's the same order as other objects like this. And I put text rotate right. Okay, in logic unit, I click on rotate right once. I place it in schematic. I'll need to push these wires a little bit for them to fit, and I put the rotate right here. And input is again A. Carry in is taken from carry in. Carry out is set to carry out multiplexer, and the result is forwarded to the last position of multiplexer. So A, rotate right means push all bits to the right, push carry into the top position of output, and store bottom position of input to carry out bit. So if I select operation number 7, the last operation, then let's see, all bits are shifted to the right from A. Bottom bit of A is sent to carry out. So if I change it, carry out changes. And top bit is set equal to carry in. Okay, so this is our logic unit. And let's make its schematic symbol as similar as possible to arithmetic unit symbol. So for arithmetic unit, here is A, B, carry in. Here is operation selector. Here is carry out. Here is V overflow, which is not available in logic unit. And here is the result. So in our logic unit, we go to subcircuit view, we make it bigger. So this is carry, it will be on the right side. This is B. Let's see, I want it to be as similar to arithmetic as possible. So it's 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. So it's like this. This is output Q. It's located somewhere here. This is output carry out. So it is located approximately here. Here is some small dirt. I don't need that. So compared to arithmetic unit, they look pretty similar. Okay, so I place text, logic unit. So this is A, this is B, this is carry in, this is operation selector, here is carry out, and here is the result Q. Okay, so this is our logic unit. That is all for this lab.